Hello, and welcome back to another video with ItsDrDan. And today we're going to be learning about exceptions to the octet rule. So we're going to be explaining this today with Lewis structures and being showing when the octet rule breaks and fails. So one thing that we were told in the very beginning of chemistry is that all elements follow the octet rule, meaning that they always want to have 8 valence electrons around their outermost layer. And the thing about that is when they do this, they want to bond with things through ionic covalent bonds. But the thing about it is it doesn't always work the way it should. There are exceptions to this rule or violations of the rule, meaning there's other things that are possible. Sometimes you might see that they don't always quite follow it. So when does this happen? What are the different types? Well, there's 3 times that you will generally see this happen. There are the 3 instances. So the first one we're going to talk about is the incomplete octets, meaning there's just no more valence electrons to make any more bonds. We just can't do it. And the thing is, those elements are perfectly happy the way they are. They don't need to have 8. They are okay with the way they are. Sometimes you might have an odd number of valence electrons, meaning that you also can't quite get there. And usually these are some of the most reactive molecules possible that are going to try to find something else to bond to make that happen. So we're going to show when are those possible. Now that's probably the rarest instance for, especially for introductory chemistry. It's a little bit more common to see it in general chemistry or maybe even organic, but it's very, very rare that professors and teachers give them to you as. So 3 is the expanded octet, which is when you have too many valence electrons. And essentially, as a result, you can make many different bonds, or you can have like these very unique molecular shapes that are being formed. This is the most common one that's seen in general chemistry. It's given as examples, especially when you're about valence shell electron pair repulsion theory or VESPR to be able to pick out shapes. All right, so let's take a look at these. We're going to go through different examples. I'll try to explain them the best that I can. And thank you so much for stopping by. And let's take a look at. All right, the first example is incomplete octet. So this is when we have too few valence electrons. So when does this happen? So this is typically on when we're in the very early parts of the periodic table. So for example, boron, which if you look at that on your periodic table, it's on the 3rd column of your main group elements, meaning that it only has 3 valence electrons around it. So being that this is a non-metal, it's going to have a tendency to want to bond via covalent interactions. So if that's to happen, let's say I have boron around some hydrogens. So hydrogen, we're going to put 1 on each side. We're going to put the 1 valence electron for hydrogen. And when we connect all these bonds, you might kind of see that there's a little bit of a problem here. So if I count all of the dots around the boron at the moment, so we only have 1, 2, 3, 4, 5, 6 individual dots around boron, meaning that we don't have 8. And you know what? That's okay. That's perfectly fine to not have 8 case. Ideally, you always want to have an octet if you can get there, but in this situation, we don't have one. So this is where it's deficient. It doesn't always have the opportunity. Another example of this would be, let's say if I had boron with fluorines. And now you might be thinking like, oh, can fluorine give some of its extra electrons? Remember, fluorine's really greedy. It doesn't want to give any of them away. So, and also fluorine has a tendency to only want to make 1 bond. So if I were to put all the lone pairs for a fluorine around it, you can see it only has room for 1 bond. So it's only going to make 1 in this case. All right. So once we connect all these our uh, our bonds here and write them all in, so drawing all of our dots. Okay, we'll connect these with a little yellow line to show our bonds, like so. And once again, you can see that it only has 6 dots around boron again. Fine, and all of the fluorines are happy. They have all of their valence electrons, so it's perfectly okay the way it is. So sometimes that is possible, and you might get a deficient one. Another example, sometimes like beryllium can make that has deficient octets. One of the most actually common ones is thinking about the Duet rule, which is when I refer to how many valence electrons hydrogen and helium have. So technically, they don't have an octet, right? They can only have a total of two valence electrons. So if we're to look at two hydrogens and we were to connect them with a single line, well, essentially each hydrogen only has two valence electrons around each of its orbitals as it's bonding with another species. So, and it's fine with that. It has a complete level. And the big reason is think about the 1s orbital, right? When we're thinking about how we draw our orbital diagrams. Well, if each one of them has essentially a 1s from each side trying to bond together, right? And we were trying to show that when they do bond together, they would each give a single electron from each side, just like so. Right? So they'll each add their own when they are bonding at a lower level. Okay, so that's something that's a little bit farther along, but they will each share one. Happy. All right, let's take a look at our next example of what else can break the octet rule. All right, so when else can the octet rule potentially break? Let's look at this one. It's when we have an odd number of valence electrons. So when you are writing a Lewis structure, one of the first steps you should do is count your valence electrons. So here, if I'm to follow that, right, nitrogen has 5 valence electrons, oxygen has 6 valence electrons. And if you find yourself that you're wondering where those numbers come from, you're counting your columns of the main group elements. So the two towers on the periodic table. One of those things is if you are trying to watch this video and understand it, make sure you do understand those valence electrons. They're used all the time with Lewis structures. So when we add these two together, we have a total of 11 valence electrons because we want to show what the structure is for nitrogen monoxide, which is a greenhouse gas. It's one of the most reactive greenhouse gases. So what we're going to do here is we're going to draw each of those dots around each of the respective atoms. We have 5 around nitrogen, and then we have 6 around oxygen. Okay. So when I do that, what we're going to first do is we're going to connect with just a single bond, and we notice neither of them are currently happy. Oxygen has a total of 7 dots at the moment, right? So if I kind of count these, we have 1, 2, 3, 4, 5, 6, and 7. It needs one more. So what we're going to do is we're going to make a double bond. So let's move around. And as a result, we'll have an 8th electron here. And then we will write our little double bond like so. But the problem here right now is if you kind of look, is nitrogen currently happy? And the short answer is kind of not, right? You see, it has 1, 2, 3, 4, 5, 6, 7. Something is wrong. It's missing, right? And where can it grab it from? It can't just steal one from oxygen because oxygen's perfectly fine. It doesn't want to all of a sudden give one up. So this is where formal charge is something that will be a factor here. So we could calculate it. Does the structure make sense the way we have it? Well, let's do it for oxygen. Well, it has 6 valence electrons. It has 4 lone pairs, and it's currently making 2 bonds. So that has a 0, so that's fine. Now, what about nitrogen on the other side? Well, nitrogen has 5 valence electrons. It has right now 3 lone pair electrons, and then it is making 2 bonds as well. So it also has a 0 formal charge on the left-hand side. So formal charge wise, it's actually what it thinks it should be. So what does that mean about this molecule? So NO is what we refer to as a free radical, meaning like your radical is like rock on. It's like kinda. It's like, oh, so what these are is when it comes to chemistry is that there's very few molecules that exist that are like this. One of the things I said earlier is that this is a greenhouse gas, meaning that these are pollutants in our atmosphere. that are very, very harmful to our atmosphere. So this one is essentially when they have very few of these are stable when they have an odd number of electrons. Most of them are extremely highly reactive. The second they come in contact with something, they're going to react. This is one of them. So usually they are very rare to see them in a general chemistry course, maybe even organic chemistry as well. So very rarely does an instructor assign you one of them. But if you do have one, keep in mind they react right away. So if an NO came in contact with something, they would immediately try to take an electron from that thing and react because nitrogen wants the octet. So it's going to try to find that extra electron. Okay, so that is another example. Let's take a look at the last one. The last type of octet rule violation that you will see is when there's an expanded octet, meaning that there's too many valence electrons. So from right here, what I'm showing you is this is the most common form that you will see in a general chemistry course. And it has to do with exactly where are these elements on the periodic table. So let's talk about why. So on the left, I have PCl5, which is a real molecule. You might get PCl5 on an exam and you're like, draw it. What is the structure of it? This thing is real. It exists. On the right-hand side, I have NCl5, which is wrong. It is not possible. You can't actually have it. So why can I have one and not the other? Both of them have 5 valence electrons for their central atom. Phosphorus has 5, so does nitrogen. But why is one possible and not the other? And just to kind of see that, right, they are both in the exact same position on the periodic table, right? So that tells you is that in thinking of those different trends, is that if I were to kind of label these guys, is they both have the same number of valence electrons, right? We got 4, 5, 6, 7, 8 valence electrons. So they have 5. So what's the difference between one? Well, one of them is on the second level, one's on the third level. So if you kind of remember all of our rows here on the periodic table. So we got 1, 2, 3, or the different periods that we have. This is the difference. So it has to do with the orbitals of where they are on the periodic table. Nitrogen, if you can kind of remember, has 1s, 2s, 2p. And then with phosphorus, it goes down to 3p. So I have here the orbital diagrams. The thing is, what's available. And if you remember from electron configuration, is what is your first D level? So here, notice how the D level is 3D. This is 4D. And this was the third row where phosphorus is. So that's important. So what that tells you is that on the third level, the d electron orbitals, they're there, but they're vacant. It's like having an entirely empty house that's been fully refurbished, fully remodeled, ready to be moved in, and they're like, you can move in for free if you'd like. And you're going to take it, right? Essentially, you have that ability there. So what's going to happen is being that 3D orbital is available, it allows it to be able to expand its octet and to bond with more things. So now the whole idea here is with that availability, there's only so many bonds that are realistically possible. So it's kind of the way to look at it is, let's say if I take that 3s electron and I move it over here to the far right to the D, notice how we have 5 spots available for bonding, right? Needs one more electron on each of the different orbitals that are here. So I can kind of add in all of these blue electrons just to illustrate, hey, we could have an extra one. So 5 bonds are possible as a result. Okay. And that's the most important thing. So what that means is that the third row of the periodic table is important. So if you're at the third row or below, they can expand their octet and bond based on how many valence electrons they have. So phosphorus has 5 valence electrons, meaning it can make 5 bonds. If you think of sulfur, which is next to it, can do the same thing. It can bond to 6 different things. Heck, even iodine or bromine or chlorine, they can bond to up to 7 things if they were to choose to expand their octet. It's a little funny. Even noble gases are actually possible for them to expand their octet and bond. Oh, um, so this is generally, when does this occur? Does it happen all the time? And the answer is no. It only occurs when you have a very electronegative element like fluorine, chlorine, or bromine, and there's a lot of them that are trying to find their extra electron any way they can, and they'll try to sneak their way through a bond. Okay, so that's what we're going to be seeing. So we're going to do an example of that next so that we can illustrate that so you know how to come across this type of problem. Okay, so let's go through an example of how to draw a Lewis structure for SF6. So when we're going through this, we need to make sure we're keeping track of every single element. So the first thing we're going to do is we're going to count our valence electrons. So sulfur, that's going to have 6 valence electrons on each of for the one sulfur. And then fluorine is going to have 7 valence electrons on each fluorine. So the next thing we're going to do is we're going to assign a central atom. Now, what we're going to assign this off of is one, what can make the most bonds? And sulfur is one of our elements that's on the third row of the periodic table. So sulfur can actually make a total of 6 bonds that's around it. So we're going to draw 6 dots around it, and it's going to bond to the 6 fluorines that are here. So now the third step is we're going to draw our fluorine and connect each one of these around our sulfur. So let's kind of draw all of them around. Okay, so we're really fast, drew that really quickly for us. That way it saves a little bit of time. So one thing you notice, I assigned all the valence electrons for each element here. So we have 6 yellow dots for sulfur, 7 green dots for each fluorine. Now what we're going to do is we're going to connect them all with a single bond. So just like so. We see that they're all connected. And now the thing is, so just to double check, is we added our octet on each of the outer elements. So that was our lone pairs. And then we assign any remaining electrons to the middle. So the reason why that last step is important is, let's say if you don't quite have enough outer atoms to fulfill this expanded octet, then you shove those extra electrons on the middle one because they can handle it with the expanded level. So what you can see here is this is the structure for SF6. So this is an octahedral structure. So that's the shape of it. It has the shape kind of like 8-sided die in one way to kind of look at it. So it looks like 2 pyramids sort of inverted with one another. So this is the Lewis structure of it. So just to kind of show kind of that shape here. So if I were to kind of try to draw this the best that I can, so like so, we would put a little line to each fluorine. So this is with Vesper structures. And then you can kind of actually like see how the shape of it is. So it looks something like this, and back to the bottom, like so, and all these the other ones would connect to the bottom too. It's gonna be an octahedral, which is one way to illustrate shapes. Okay, so let's take a look at our last example. All right, draw the Lewis structure for ICl4 negative. All right, so this one's a little bit tougher because it involves formal charge and making sure that we have the right bonds. So iodine can bond to chlorines, but the thing about iodine is, remember, it has 7 valence electrons, so does chlorine. So iodine is actually capable of making 7 bonds, but we only have 4 chlorines here. So it's going to not quite match up. So it's going to involve that last step, which is step 5. So first thing is, right, is write down those valence electrons so we can kind of keep track. So we should have 7 valence electrons for iodine at the minimum. And then for chlorine, we should have 7 valence electrons for each of those. Now we have 1 extra electron, the negative charge that's up at the very top. So we'll just put 1 valence electron. We'll put that in purple just so we forget about it. Now, the first thing we're going to do is we're going to assign what is the central atom here. So our central atom is going to be iodine because it's capable, it's on below the third row or below. So this thing is going to be capable of multiple different octets. So what we'll do is we're going to draw essentially room for the 4 chlorines. We're going to have 1, 2, 3, 4. And then what we're going to be doing is putting in the remainder of the 7 electrons. So we'll put that on the sides. Now we're going to put in our chlorines, and what I'm going to quickly do is just fast forward. So we put the 7 valence electrons around each chlorine. Okay, so now that we did that, we put in all of our different electrons. Now the next step is, so that's completing our octets on the outer atoms. And then what we're going to do is then connect these with a single bond just to illustrate that, okay, we are making bonds. So we got one here, one here, one here, and here. So we'll have it on the other one. So this is going to be complete octets on all of the chlorines. So they're all happy. Now we have essentially a problem though. As you can see, there's one lone electron on iodine. But don't worry, we do have essentially our extra electron. So all extra electrons, they get assigned to the central atom. So we're going to be putting that right here like this. So generally when we have lone pairs that are on these expanded octets, usually we'll kind of push them out a little bit like this. And then it's very common to draw a little line to illustrate, hey, they're here, but they're pushed out so that way you can illustrate the structure a little bit better, just like this. Now, as a result, we can see those lone pairs are above and below, and then we have everything else on here, so we can double check our formal charge for ourselves. So chlorine, right, has 7 valence electrons. It has 6 lone pairs and then 1 bond, so that's completely happy. Now let's take a look at iodine. So iodine also has 7 valence electrons. Right now it has 4 lone pair electrons, and it's making 4 bonds. So it has -1 charge, which is exactly what we want because it was ICl4 minus, right, is what we started with. So that was the beginning of our molecule. So whenever we have an ionic species like this, what we need to do for ourselves is put it in brackets, illustrate, hey, there is this negative charge on the molecule. Okay, so we have that 1 minus charge that we have here, and then put that on just like so. Okay, so this is how the expanded octet rule can work. These are rarer examples, but typically it's whenever you have these very low nonmetals is really the key for what you're looking for. So just keep in mind, row 3 or below, they are the most common ones you're going to see. The other ones is usually when you have boron. That one's a little bit easier with when it's less. Okay, so these are 3 different types of octet rule violations. I hope this video helped you, and thank you so much for watching. Bye now.